I am Jake Wharton, and so I'm here to talk about annotation processing. And on the presentation, or the RFC, it was not just annotation processing, it was a very specific kind. And that is the kind of boilerplate destruction. Because annotation processing is a fantastic tool to enable us to automate a lot of the boilerplate that we see in our apps. And that's because I think you would all agree with me when we think of boilerplate, we all think the same thing. So I'm going to start off by highlighting, so actually in my presentation, or my proposal rather, I said that we're going to focus on existing libraries and how they can help you out. And then at the end, we'll briefly cover how to get started writing your code. So as I started talking to people about this talk and what they wanted to hear, it turns out that most people kind of know how to use annotation processors and are more interested in the underlying mechanics and how to write your own. So we're going to flip this around. I'm going to briefly cover a few, and then we're going to take a pretty deep dive in how they actually work. Dagger is the first one. Dagger is a dependency injection mechanism that is not Android specific, but the means through which it does dependency injection is very Android friendly. So this would be a piece of code that is consuming, or rather using Dagger to perform dependency injection. If you're not familiar with dependency injection, I'm not even going to try and start explaining what it is, but this class is requesting two dependencies, a pump and a heater. And the heater is using a special feature of Dagger which allows it to be lazily instantiated. And so the reason that Dagger is very Android friendly is that it actually uses code generation to fulfill the contract that this class is emitting for these two dependencies. Dagger fulfills that contract and knows how to set the dependencies on the class without using reflection. The URL is at the bottom if you missed it. Butterknife is an Android-specific one that came out of Dagger and people not quite understanding that Dagger didn't replace row juice. Butterknife allows you to inject reviews. It's not really injection, it's just eliminating the lookups in your layouts through annotations. So this will perform a find view by ID for you in your layout, do the casting. It can also do things like binding clip listeners and other listeners directly to methods. And the way through which you request this to happen is just a simple API call after you've inflated your layout. And so this also uses generated source code to fulfill this contract. So some ones that are potentially a little more unknown, hopefully, in the annotation processing world. Auto value, this is from Google. It's a very simple way to create value types, or in the absence of value types in Java, this creates almost value types. You basically use an abstract class to declare the properties of a value. So in this case, we have an animal who has a name and a certain quantity of legs. And then you'll see there's a static method which is referencing this class called AutoValue_animal. And this class is going to be automatically generated because of the AutoValue annotation. It's going to implement the hash code and toString and equals methods, which are going to use all the declared types. It's going to have, it's immutable by default. It's actually always immutable. So only the accessors here that we've declared are the ways through which you can get these values. So it's a very quick way to spin up what otherwise would be kind of complex POJOs with a lot of boilerplate. More Android specific, and in a similar vein, is something called AutoParsel. There's actually a few of these, but AutoParsel is my favorite. It's basically the exact same thing, except with a different annotation, AutoParsel, and we're now implementing the parsable interface. Except since we're an abstract class, we don't actually have to implement the parsable interface, because the generated class from AutoParsel is going to implement that for us. So now we have a very easily parsable bunch of different fields. Finally, this is a relatively new one called schematic. It's pretty ambitious, it's a little underbaked, but it's pretty cool and kind of shows the types of things that you can do. It starts off, it's for databases, so we start off declaring what is otherwise a table, or the columns for a table, and the properties of those columns. So here we have a primary key, an integer column with a reference to another table, and then just a text field. We have our database, which knows about our tables. So here we're referencing both the table that I showed in the previous slide and another table. And then it's going to end up generating actually a full content provider. So if you've ever used content providers and ever written one, you know that they embody the definition of boilerplate. It's just a ton of code. It's absolutely terrible. And so this is going to generate the few thousand lines of code that's required for a content provider for these two tables, both for querying, updating, deleting, and insertion. Like I said, it's a little underbaked, but it's a really cool idea of how you can leverage these annotation processors. Okay, so that's all I'm going to cover for libraries. We're not going to dive really deep here on the mechanism through which annotation processors work. And in order to get there, I kind of have to do an origin story. So we're going to start with something called Doclet. Doclet still exists today, but it's really old in Java lifetime. It's basically an interface, an API rather, through which you can access properties of your compiled classes. So in this example, I'm referencing the Java APIs and defining a static method called start, which takes this root doc in and returns a boolean. And through here, I can loop over the classes, say, that are available to me. And so this is the mechanism through which JavaDoc is generated, but you can leverage it yourself for doing all kinds of things. So you can potentially generate code based off of this. And this is how you invoke it. It still works today with any JDK. So Java 1.5. Java 1.5 was released in September of 2004. So happy 10th birthday, Java 1.5. And it came with all kinds of really cool stuff. Generics, which it's hard to believe these never existed. Annotations, of course. And a whole bunch of really other awesome things. I'm not going to go into them, but generics and annotations are the two that are going to be most able to be leveraged by annotation processing. And it also brought this command line tool similar to the JavaDoc tool called APT. And that stands for Annotation Processing Tool. And in order to not confuse this with actual annotation processing, we're just going to refer to it by APT. APT allows you to define an annotation, annotate a few classes, and then through executing this tool, you were able to act on the classes which implemented, or rather, which were annotated with whatever annotation. And its API was really simple. It's basically just a process method, and then a factory for the thing that does the processing. So you don't really need to kind of see what's going on here. Let's just implement it really quickly. Supported options, not going to cover. Supported annotation types. This is a declaration of what we're interested in. And then finally, we're creating basically instances of our processor. Don't worry if I'm going quickly. This is not what we're here to talk about, just kind of demonstrating where we came from. So this is the class that implements this old annotation processor, which I said just has a single callback. And now you can see, similar to the original JavaDoc tool, we can just iterate over the annotated type declarations and say print them out. And so this will produce the same thing that that initial JavaDoc, or rather Doclet snippet would do. And here's how you run it. So, 6 months after Java 5 came out with the APT tool, JSR 269 was submitted. And this is the pluggable annotation processing API. Annotation processing for short. It was backed by a few big names. The goal was to simplify and standardize processing annotations. So people have been using the annotation processing tool through the development of Java 5 and after its release, and realized kind of there were a lot of shortcomings. So that's what this was meant to fix. And the big thing was that no longer would this be a separate tool that you had to invoke. It would be built into Java C, which means it was much easier to opt in and much easier to integrate in your builds. So this was our old processing API. And it got a little crazy, and we had a few more methods that we had to care about. In reality, so we're going to go through those in the future, but in reality, what you should always do rather than implement processor is always start with this helper class abstract processor. It takes care of some of those methods for you, returning reasonable defaults. Source version, this basically tells the annotation processor the level of class file that you can support. Always just return the latest supported. And I will never mention that again. So we still have the supported annotation types method that was on the previous one, and we're just going to do the same thing. We're going to return a set of the fully qualified types of the annotations. So you see here, I'm using the actual class, but I'm getting a string name from it, and then just returning a singleton set in this case. Still have our process method. The difference here is we're no longer given all the things that have the annotation. We have to look them up. So there's this parameter called env, which we're going to talk about in a bit, and we just query it for a specific annotation. In this case, our only one, which is example. And then it's much of the same. We iterate over it. This returns a Boolean value, always return false. Okay, here's the whole thing. So how does this get executed then, since there's no longer a standalone tool? Like I said, it happens automatically inside of Java C. There's nothing you have to do to opt into this. Simply by having an annotation processor as part of your build, it's going to be run. Inside of Java C, which is actually just it's just Java code. Java C is written in Java. There's a thing called service loader, which knows how to find and create the instances of these processors. And so that means we actually have to tell service loader that we are an annotation processor. And for those that aren't familiar, this is just a brief kind of summary of what you have to do. It's basically just a file that sits, which usually in source main resources. The service that we are implementing is the JavaX annotation processing processor. And then, so that's the file name. And then inside of that file, we list the annotation processors that we have. And so we'll include our common example processor. And you don't have to worry because I blew through that. I'm going to get rid of it later on in the talk. So now that we have our processor instances, now the Java C has them rather. Oh, I just said that. One of the things that's a bit tricky is that you have to remember is that you're inside this JVM, but you don't have access to the sources and dependencies of the code that is compiling. So Java C is running in a JVM, and it's taking in your source code and spitting out class files, and those class files, to be later either indexed or loaded in the JVM. They're not part of your. You can't access them directly inside your annotation processor. But the cool thing about that is that you can bring your own dependencies into the annotation processor, which are not part of the application. And we'll see why that's beneficial here in a second. So we've covered these three callbacks for why they're there and what they provide. Supported options, also in the previous APT tool, I'm not going to cover. We have this completions callback. This is a really cool feature that is way under-implemented. It allows you to provide feedback to IDE tools. So as people are typing your annotations, even if the code doesn't compile, you can give them autocomplete suggestions. But sadly, I think it's only in Eclipse and NetBeans. Finally, we have this init method, which takes in something called a processing environment. So let's take a look at what a processing environment actually is. We have another giant interface. It's not so giant. Option source version and locale. Not super important. We have something called a messenger. This is the way through which you communicate back to either the command line or the IDE that is doing the compilation that your annotation processor is in. So you can provide information lines just saying things that were processed, and you can also trigger warnings and even fail to build just by triggering an error through this messenger. And that will build where it's quickly in the implementer's IDE. We have something called a filer. This is the way through which you access the file system for generating code or any other resource. And then we have these last two, which are kind of two halves of the same pie, elements and types. And these are helper classes, which we're going to see that we will heavily lean on. So elements and types are one of the hardest things, I think, to get a grasp on for annotation processing. So this is a piece of code that is using our example annotation. And what we're going to do is take a look at the elements that comprise it. So elements are basically a representation of pieces of the syntax. So I have a type element, which is what the class basically is. It represents a type in the syntax. Inside of that type element, as a child of that type element, I have a variable element, which is this name field. I have an executable element, which represents the constructor. And then I have another executable element, which represents this method. So when I look up the example annotation, I'm going to be given back a type element, and then I can say, get enclosed elements, and it will return a list of these three pieces that are inside in the syntax. So like I said, type elements refer to their children, or rather all elements can get their children. And then if you have an element, so say I'm at the run methods executable element, I can actually go backwards and I can say, what is the enclosing element that this piece of syntax is enclosed inside of? Types are types refer to what the actual pieces of code represent. So we don't have, like I said, we don't have access to this class instance inside the annotation processor because it's being compiled. But what we have access to is it's a representation of its type. So the example class is a type. We would get what's called a type mirror for it, and it would represent a fully qualified type, including the package name, which is not up here, but it's talking about example. So we would basically know what the fully qualified class would be for the class file that's being generated. The interface that's also implemented, we can get the types of the interfaces. Also, if you're extending classes, you can get the types of the superclass. The field has a type. When we have the executable element for the constructor, its parameters have types. And then the method, actually the return type, even though it's void is actually a type. We can get access to that and query it. That's probably the hardest part, understanding the distinction and understanding how to move between types and elements when you're inside the annotation processor. So if you remember, I wrote this. This is actually a bit incorrect. In the Doclet and APT version, I was printing out the fully qualified class names of the annotated classes. And you'll see in the for loop, I'm looping over the elements, and the elements only represent the syntax, not the actual type. So when this printed out, I would only get the class name, basically. So what we need to do is switch this and pull the type that the element is going to represent, pull that up, and now when that's logged, we'll have the common example class. So I talked about using the end, this round environment argument, as the mechanism through which we look up classes that are annotated. So let's take a look at what a round environment is, and why we have to care about, and why we need it. Yet another interface. But we only care about one method, really. You might use the others in more advanced cases, but really this is the one through which you're going to be doing most of the communication with the round environment. And that's the one that we were using, the one to look up elements with an annotation. So the reason we have a round environment is that there's this thing called processing rounds. And I'll show you why they're required using our example. So we have our class is annotated with the method that we've written process it for. And that's going to get shoved into Java-C. Java-C is going to start running, and it's going to find our example annotation processor and our hypothetical other processor that I've included in. And so compilation is going to start running on Java-C. And it's going to do what you would expect. It's going to spit out a class file. Our example processor is going to run, and it's going to generate this hypothetical code, which has our other annotation on it. Our other processor is going to run, but you'll see that the inputs into Java-C don't have any other annotations, so it has nothing to do. Now there's nothing left to process, and what would normally happen if we weren't doing this would be Java-C would exit. But that's not what we want, right? We spat out a class file that's a source file, rather, not a class file. We spat out a source file which has not been compiled. So we actually couldn't use generated class in our route. What actually happens is that the filer notices that a source file was emitted, and it's going to trigger another processing round, and it's going to return that class, that source rather, into Java-C for compilation. So we spit out our generated class. Example processor runs. In the inputs that we got here, there's nothing to do. But now our other processor is going to run. And it's going to spit out some other generated source file. And so you should start to see why these rounds are necessary. Because multiple annotation processors at different times can generate source files which require compilation. So this is going to end, and we have to do one more. Thankfully there's no annotations. Generate our class. Both annotation processors run, but there's nothing to do. And now Java-C can exit because it's done the compilation. It's compiled all the generated source files, and all we're left with are the three classes. I'm going to illustrate that again on a timeline here to make it seem more clear. The Java compiler, like I said, gets initiated, and it finds our two processors. The processing environment and its file that it has, also its the messenger and the other stuff, which are not relevant, get instantiated. And the processing environment then calls the init method on those two processors in order. But we can't guarantee the order with which they're initialized. At this point, our source files are injected into the Java compiler for compilation, and we spit out class files into the file system. But what we also know happens is that one of those files contains an annotation, so we have to start a new annotation processing round. We trigger a callback on the example process method with this class file, or not the class file, rather, the representation of the source file. And through that, we generate the code, and our round ends. And then like the additional round showed on the previous slide, we go through the same thing in order to trigger the second round, in which the other processor is going to generate code. And then finally, we put that into Java-C, init in its class files, and that's it. Okay, so let's take a look at our processor more closely here. One of the things that is normally done when you're writing an annotation processor is you grab these elements and you want to hack them. So here I'm iterating over my elements, and maybe I'm seeing some property of them, and I want to write out generated source files from them. So I interact with the filer directly and write out these source files. This is certainly fine for the trivial case, but it's not a good pattern to get into. So what instead I'm going to recommend is that first we go through a step of doing elements are representations of the syntax, and what you really want is kind of representations in your domain, things that you care about. So we're going to create a model based on the properties of the elements only that we care about. And I'll show you why. And then we move over them and emit code through some method. So why would we want to do this? So we have our element. Maybe we actually have 10 elements. The reason we want to parse this into a model is that we can pull out properties that are not directly accessible, but that we need to access. So you'll see the package here. I've included the package and I've included the visibility of the class. So in this case it's public and it's intercom example. Oh, I forgot to tell these. And what we want to also do is include the original element inside this model so that we can refer back to it. But what we've done is we've parsed out all of the properties that we really care about for generating code or validating code. And the reason is because accessing things like the fully qualified package name is not just a trivial method call on the element, and it's not something you want to be doing constantly while, say, you're generating code. So we pull this into a nice immutable model, hopefully. And then after having that, we can generate our classes directly from that model. So this gives us good separation of concerns. And it also aids in doing things like unit testing your annotation processor. Yeah, so we see here, we basically isolated this step. So going back to the bring your own dependencies, annotation processors can certainly be written in a vanilla fashion with no dependencies, but I would highly discourage it just because of the type of work being done. There are great libraries out there to really assist in this. Guava being the big one. Some of you may probably don't include Guava in your apps, so this is a great chance to actually lean on it hard for all the benefits that it provides. There's one called Java Writer, which I'm going to go through. This is a way through which you can generate source files much more easily than doing something like String Builder. In the repository of auto value, which is by Google, there's actually 2 other processors. There's about to be 3. And there's also a common module which includes helpers for writing annotation processors that handle some of the more complex things for you. And one of those others is called auto service, which I'm going to learn. Let's talk about Java Writer first. Java Writer is going to allow us to very easily generate code. So I'm referencing the filer here, which is that object that we access from the processing environment to generate code. So this is the method that we call when we create a new source file. So I'm passing in the fully qualified name of the class, and the second argument is actually a var args. We can pass in multiple elements. And these elements are the originating elements from which the source file is being generated from. So in our example annotation, we would pass in the element of the example class. And this is so that Java-C rather can do smart things like incremental compilation when source files change. So we get a Java file object. Through that Java file object, we're just going to open a stream and wrap it in Java Writer. And that's going to give us this nice fluent API to emit source code. So you'll see I'm splitting out a package, the other annotation, the generated class, which is a class, a comment, which just has 3 dots, and then I'm ending the type, which is the class. So it's going to spit this out. It'll have a package, which I didn't include. But the cool thing, and one of the great reasons to use Java Writer, is that it can be a little bit smarter about things like imports. So if I modify the code above, and I toss in an import for the other class, when it reaches the emit annotation, it's going to see that an import was emitted for that fully qualified type, and that means that it can omit importing, or rather referencing the fully qualified annotation in your source file. So some of you might not think this is useful, but one of the things that we value very highly in writing these annotation processors is having code that gets outputted that is very human readable, very friendly, almost to the point where it's the code that you would just write yourself if you were doing the job of the annotation processor. So we value things like this because when you're writing these classes, if you're writing these classes, you're going to be using that import. You're not going to reference annotations in a fully qualified fashion. So auto service. So I blew through the service loader part at the beginning of the slide. That's because you actually don't have to do it. Hopefully, auto service is going to blow your mind a little here. We're going to get a little conception-y. So auto service is an annotation processor that's going to generate service files for you. So it's going to generate this any of these files inside the metadata services folder. So here's our annotation processor. And before, we would have to create this file manually and put in a reference to the class. With auto service, all we have to do is annotate our annotation processor. And we give it a reference to the service that it implements. So even though we're sending abstract processor, we're actually implementing this JavaX annotation processing processor. So we give it a reference to that. And when our annotation processor source code is being compiled by Java-C, it's going to generate that in-services file so that when that jar is included on the class path of Java-C that's compiling your app, it can find the annotation processor and run. Pretty gnarly, pretty awesome. That's in the auto repo. So one of the pain points of annotation processors are testing and debugging. So let's go through what testing looks like. And yet again, Google to the rescue. Once again, Guava is a huge friend here. And I like it so much, I put it on the slide twice. Really amazing things in here, especially in the collections package, in order to create these models and test them. So there's two other libraries that are from Google. One is called compile testing, and the other is called truth, which is an assertion library, but it's a little more tailored to advanced assertions rather than just, say, comparing strings or objects. So the first thing we do to test an annotation processor, we're going to create this helper class, which we're going to end up using in every single test. And all it's going to do is have a helper method to create a list, rather an iterable, of instances of our annotation processor. So here we only have one. If we had our other processor, which we were also testing, we would just include it here in whatever order we wanted. Then we're going to create source files in strings. And this is because what we're going to end up doing is compiling this code and asserting on the output. So here I'm just using Guava to join a few strings together. You could also just be concatenating these. We're going to create this thing called a Java file object. You might remember from when we were interacting with the filer that this is the same type. This is the same type of the filer gives you back. So we're giving it the fully qualified class name here, and then the string representation of the contents. I also recently learned that Groovy has this awesome feature where you can do multi-line strings and then chop off the indent, which is also whenever you're testing Groovy, it's pretty gnarly. So now the other half of the equation, the output code. Here you can see our generated class. I forgot to include the comment. But it has our other annotation and our import on it. And we're going to do a similar thing where we create this Java file object, which represents the output class. So here's how you are going to produce the output class. So this assert method here is a static import. This comes from the truth library. And then we're going to pass it another static import called Java source. This comes from compile testing. It basically represents the fact that we're going to be putting in a source file object and then asserting things on its output when it's run through the Java compiler. So we have our input class. That's our input file. annotation processor as the process with command. So it's going to take our input file, it's going to process that source file using the annotation processors we provided, and we're going to assert that it generates our output source string. And you'll see it also includes a compiles without error, which asserts that Java-C, or rather the Java compiler, exited cleanly. And so this is really cool because what it's going to do is actually run the Java compiler in process as if it was running inside Java-C. So it's going to take your source files, run the Java compiler, and assert the elements. And so this is a very trivial case. You can imagine you can do much more complex things with multiple input files and asserting multiple output files. You can also assert errors. You can assert compilation errors. So here we're compiling without an error. We can assert that the output failed to compile, and we can assert that it emitted, say, a warning that annotation couldn't be used on this field. And what's really great about the fact that this Java compiler is running in memory is that means that this is the way, pretty much the only way through which you can actually debug an annotation processor. Because normally the annotation processor is running inside Java-C, you don't have an avenue to hook into it to attach a debugger. So now, in my example processor, if I'm running that test that we just did on the previous slide, I can set a breakpoint, and this breakpoint will actually be hit, and it's going to allow me to do things like query the elements, see their children, which is extremely useful because, like I said, the elements and the types are one of the hardest concepts to get used to in the annotation processing environment. And so now, basically that's it. And I don't have anything else. But all I have is that I implore you to kind of take this knowledge and think up something crazy. The schematic library is a perfect example of starting to push the boundaries of what you would use an annotation processor for. I would actually argue that it's probably not the best use, but the fact that it's being tried and being experimented with is really awesome. This is an underutilized feature of the Java compiler that's been around for quite some time now, and I really would like to see a lot more libraries coming out, whether they're public and open source, solving some kind of problem, or even internal. The code that you write that's very specific to your app absolutely is going to have some form of repetition or something that you could automate either through something like a plugin or a standalone script, but maybe potentially even through an annotation processor, which is going to be much more compile time safe and provide much better feedback to you as you're developing an IDE. Another thing that I didn't really touch on was this can be used solely for validation. So generating code is always the sexy side of annotation processing, but you can use it solely for validating aspects of your code. So maybe you have an annotation that just checks a certain way that a class is being used or where it's being used. You can use the messenger, which is part of the processing environment, to relay messages back to the IDE about how those things are being used. To this animation film. So, with that, I will take any questions. So our type of element is the same as used by plugins like an IntelliJ. I have written a plugin, I've contributed to a plugin or two, specifically to like IntelliJ. All their stuff is like PSI, whatever. I actually don't know if they're the same, but a lot of people also often correlate them with the reflection-based classes like constructor and method and everything Java lang reflect. Because these are representations of syntax and conceptual types, they're a wholly separate API. So I actually don't know if plugins use these, if IDE plugins rather actually use these packages, but they're just part of the standard Java JDK. So there's nothing technically prohibiting them from it. But I think just because of the level of integration that IDEs require with the source code, if they're using them, I think they probably end up wrapping them inside their own specific types, like intelligent PSI, PSI classes. Or really the static method on those classes was referencing directly to generated code, whereas something like Butternut or Dagger 1 was going to use a class, a runtime library to look up those classes by reflection, and whether or not that's a good or bad practice. So I don't know. I prefer the reflection-based approach for its simplicity and the fact that it allows your code to be completely ignorant of the implementation of the annotation processor. Really, the reason that auto value specifically went through the direct approach is focused on speed, basically, in the absence of a runtime library. That being said, Dagger version 2 currently requires you to reference the generated code directly, which we don't really know how we feel about it yet. I think there's room for both, and it really just depends on the requirements. I think the auto value is on the extreme side, where it's something like Butternut, even though it's using reflection to find that class, it's caching aggressively. And reflections being, as long as it's something like layer inflation is happening sporadically, maybe 50 to 100 times in an app lifetime, whereas using auto value might generate thousands or tens of thousands of instances. And so it really just depends on how the annotation processing generated codes can be used at runtime. Because I totally agree that it's really weird to write code that depends on generated code that can't be generated until you wrote the code. Because it's a classic cyclic dependency, and it works, but I don't know if it's an ideal experience for everything. So having that reflection shim is a really convenient thing for a developer, although maybe not for performance. Yes? So, I mean, how does the Dagger compiler work with the Java compiler? It's certainly a non-trivial thing to kind of explain. It goes to that slide where I talked about the model, basically. Because Dagger usually proliferates to a bunch of different classes, it almost always has to deal with things like only partial classes being represented that's being compiled, or and through that, the reason what we do is we have to pull those things out of the model so that we can reason about them and understand that we might not have access to all the types being used. Because, class values in, say, a jar might be being used, we might be injecting those things, but those types actually aren't